afternoon or good morning according to your time zone. Thank you for attending today's webinar. We will talk about the flat dilatometer, the seismic dilatometer, and the Medusa SDMT. I will deliver the first presentation, and the second presentation will be delivered by Professor Sara Moroso from the University of Chieti Pescara and a cooperator at INGV of Italy. So this presentation will have a brief introduction and then focus on the flat dilatometer, the data interpretation of the flat dilatometer results in terms of formula, showing validations and comparisons. Then we will look into the seismic dilatometer and then the Medusa SDMT. Finally, I will show some case histories and examples of results to show how to read the results of this test. So, soil characterization plays a key role for the optimization of geotechnical design. The target is to obtain reliable and high-quality soil parameters, and the method consists in employing the appropriate testing technologies according to the soil type, specific geotechnical application, and project risk. So the aim of this presentation is to describe the DMT, SDMT, and Medusa for in situ testing in terms of equipment, test procedures, results, and also recent innovations, and when it is appropriate to use it and when it is not. So let's start with the flat dilatometer. The dilatometer is a blade that is pushed into the ground using penetration rods and with a pneumatic electric cable that runs from a control unit into the penetration rods and down to the blade at depth. The black arrow represents penetration machines that we will see in the next slides to advance the blade into the soil. A gas tank of compressed air or nitrogen is required to supply the source of pressure for inflating the blade's membrane. A computer is generally used to have a data acquisition of the test readings in the field. Now, the test procedure consists in starting from ground level and pushing every 20 centimeters and stopping. Initially, the circular membrane of the blade will be flat against the blade due to the total horizontal stress of the soil acting on the membrane. The operator will inflate the gas that will travel into the pneumatic electric cable and inflate the gas from the inside of the membrane. When the pressure will be in equilibrium, the first pressure reading A will be taken, which is called also the lift-off pressure, because the membrane lifts off from the plane behind it. The operator will continue to inflate the gas, the membrane will expand, and when the center of the membrane expanded 1.1 millimeter in its center, the second pressure reading B is obtained. The operator must then deflate after B to avoid the membrane to overinflate or to break, and the membrane will return into the original position. If the deflation was performed with a slow vent valve, the C reading, which is the closing pressure of the membrane returning after B, will also be recorded. So a DMT test consists in taking 2 or optionally 3 pressure readings, A, B, and optionally C, every 20 centimeters. These are the main components for the traditional pneumatic DMT test: the gas tank, cable, control unit, and blade. The blade is a stainless steel blade with a flexible membrane of 60 millimeter diameter mounted on one of its sides. As we said, when we push it into the soil, initially the membrane will be flat and the audio contact signal will be on. When the operator inflates, we will build the pressure from the inside of the membrane, represented by the blue arrows. When the pressure of the gas is in equilibrium with the total pressure of the soil in the horizontal direction, the membrane will lift off, the contact will go off, and the A reading is taken. Inflation continues, the pressure inside the membrane from the inner side increases, the membrane expands. When it expanded 1.1 millimeter in the center, the contact returns on and the B pressure is taken. Basically a horizontal load test to arrive to B. Then deflation occurs, the contact goes off, and when it returns on, if the deflation was done with a specific valve of the equipment, then the C reading will also be taken. The most efficient and productive way of performing a test is to use a heavy truck penetrometer, which is able to advance the blade into the soil without lateral instability up to 20 or even 25 tons of push. Other effective methods are light penetrometers, like this light penetrometer you see in the picture, which is able to push even 15 or 20 tons, but its weight is much lower than a truck, so if it pushes more than its weight, it will lift. Some of these machines are able to anchor in a depth in order to get the reaction force and push a little more than their weight. The better it anchors, the more it is able to push. There are many other possible ways of advancing the blade into the soil, including dynamic with an SPT tripod, although it's not recommended, at least not in soft soils. In hard soils, it is possible and the results are very similar. Or it is possible to push from the bottom of a borehole with a drill rig, just like an SPT test. Or any way we can think of, as long as we advance the blade in the virgin soil, where it has to measure the soil parameters. One of the most common methods of advancing the blade alternatively to penetrometers is to use the torpedo system. The torpedo consists in pre-assembling a blade with penetration rods, usually 3 or 5 meters according to the height of the drill rig, and using this top adapter with a slot for allowing the cable to pass inside these penetration rods and then coming out of the slot and taped with standard tape to the drill rig rods. So a borehole is performed, and then this torpedo with the cable is connected to the drill rods, lowered to the bottom of the borehole, push every 20 centimeters and perform the measurements. And then when the height of the torpedo is concluded, everything is taken out, the tape is cut, the cable is taken, and the torpedo, without disassembling it, is lowered on the floor, advance the hole to the next depth, advance the casing, and repeat. So this test, of course, is slower than a penetrometer, but it allows to have a productivity of about 40 meters per day. But the advantage is that if there are obstacles, like layers that are not penetrable, with a penetrometer, we hit refusal and we stop the test. With the drill rig, it is possible to drill the impenetrable layer and continue below. So this is an example of an alternation of penetrable and impenetrable layers. You drill the impenetrable layers, and the measurements are performed only in the penetrable layers, pushed with a drill rig. You want to have at least 3 or 4 measurements, so 60 or 80 centimeters of penetration to confirm the readings in that layer. The profiles will of course exhibit voids where the layers are not penetrable, but the trend of the soil parameters is quite clearly visible. So it may still be helpful. And definitely in many projects where there is penetrable and impenetrable layers alternatively, the softer layers are the ones that are most critical for design. The DMT test may be performed in all penetrable sands, silts, and clays where the grain size is small compared to the membrane diameter of 60 millimeters. This means from a range of very, very soft geomaterials with very low value of strength and moduli, up to very hard soils to the limit of soft rock. We have readings with on drain shear strength of about 1 MPa and moduli of about 400 MPa. The blade is very robust, and it is the same blade in soft and hard soils. It is possible to push it up to 25 tons, and as you see here in the concrete, it can even break obstacles of concrete. You don't want to make measurements, of course, in rock or concrete, but the blade is not going to damage. Normally, the critical part in damages is due to the rods, which may bend and break um, if there are certain conditions on site. The test with the DMT is not recommended in gravel unless there's only a few components of gravel in a matrix of finer material, like sand, silt, or clay, again, with some parts of gravel which will move away. And of course, the test is not recommended in rock. Now, the test can be performed also offshore, either from a jackup using, for example, a drill rig, like in this project of Venice for the mobile barriers, or in this case, a lake from a floating barge using a drill rig, or with a penetrometer on a floating barge. Any configuration is possible. Currently, we are working at the project in Genova Harbor with 50 meters of water, and in this configuration, there is a floating barge with a crane and lowering a seafloor penetrometer, which is lowered to the seafloor, and using the Medusa DMT, perform the test starting from the seafloor. One of the most fascinating project we participated to was in Norway. In this case, the Medusa DMT and the seafloor penetrometer of the Manta was combined for operating up to 1,000-meter depth of water. Now that we have seen the introduction on the equipment, let's have a look at the interpretation of the results. We said that performing a DMT test consists mainly in performing A, B, and optionally C readings every 20 centimeters. Let's see how it is possible to obtain geotechnical parameters. To do so, I must first introduce the concept of membrane calibration, because the membrane itself has a rigidity due to the fact that it is of steel and it has to expand. So even though calibration is an incorrect term, historically we talk about membrane calibration, but the most correct and appropriate word would be tear, just like when we weigh the food and the container and then we subtract the weight of the container and pay only the food. The container weight is like the rigidity of the membrane that must be subtracted when the tests are performed into the ground. So just to give you a few notions on this, when the blade is out of the ground, it's in the intermediate position between A and B. No one is expanding it to B. No one is pressing it in the A position, so it's in an intermediate position. And so we perform basically the A reading, which in free air is called delta A, applying a suction, and delta B by inflating gas and expanding to B. And these readings will basically be subtracted to obtain the net readings. So the first step of the processing of the field readings A, B, and C is to get the net or corrected readings A, B, and C that are named P0, P1, and P2 by using the calibration values delta A and delta B. The second and most important step is to evaluate the DMT intermediate parameters, which are ID, KD, ED, and UD. To calculate these intermediate parameters, also the vertical stress and the water pressure are provided into the program. These evaluations of intermediate parameters go through definitions, not through correlations. So they have no degree of uncertainty. The correlations come into play when from these intermediate parameters, each of which has a specific meaning in terms of soil behavior, and we will see this in the next slides, then Professor Marchetti provided the correlations to the standard or close to standard geotechnical parameters, in particular the ones you see here. So the constraint modulus, the undrained shear strength, earth pressure coefficient over consolidation ratio, friction angle, unit weight, pore water pressure in sands, and the distinction between drained and undrained behavior of layers. So for this, there is a set of correlations that I will show you in the next slides. So this is a summary of the formula, As you see the field readings, we saw them, A, B, C, and the calibration. We will see the dissipation test later on. The corrected readings, P0, P1, and P2. The intermediate parameters, ID, KD, ED, UD, and the flex point for the dissipation test. And then the interpreted geotechnical parameters that were proposed by Professor Marchetti in 1980 and that are still used today as standard formula for data processing of the DMT. The table and the chart on the right shows how two information are obtained from two of the intermediate parameters. On the x-axis, you see the material index ID. On the y-axis, you see the dilatometer modulus ED. So according to where you spot on this the point on this graph, on this chart, you will have two information: the type of soil. For example, if we're on the S of silty clay, it will be a silty clay, and the number in the box 2.05 determines the unit weight, an estimation of the unit weight expressed as a ratio of unit weight over the unit weight of water. Now let's look at the main intermediate parameters and their correlation to estimate OCR, K0, M, and strength parameters. So if we perform a DMT test in the field, we will immediately notice that the A and B readings, which are very similar to P0 and P1 with the corrections of the corrections of the calibration, the ratio B over A or P1 over P0 is about 1.1 to 1.3. If we are in sand, the ratio P1 over P0 is at least about 2.5, and of course the silt falls in between. So Professor Marchetti defined the material index ID as the difference P1 minus P0 normalized to P0 minus U0. Just to show an example that is more intuitive, if we look at this test near the airport of Rome and Fiumicino, you see that in the sandy layers, the second reading is about 4 to 5 times the first reading, whereas in the clay, below that, at 19 meters, the ratio between P1 and P0 is about 1.1 and 1.2. The second intermediate parameter is KD, evaluated as P0 minus U0 divided by the effective vertical stress. So it relies only on the first reading, not on the second reading. The formula looks very similar to K0 if P0 minus U0 were the effective horizontal stress. But it looks like, because P0 is the total horizontal stress, minus the water pressure should be the effective horizontal stress. Unfortunately, this is not exactly true because we have penetrated with the blade and increased the water pressure and the horizontal stress with the penetration of the blade. So KD has been defined as an amplified version of of K0 because P0 is an amplified version of the horizontal stress. However, we will see that KD is very, very well correlated to K0 and OCR in clay, especially, and that it is probably the most close measurement of K0 than any other method possible and faithful to the original state of the soil in situ rather than in laboratory. So it is possible to read the KD parameter in clays so that if the value is equal to 2, the soil is a normally consolidated clay. However, if the KD is higher than 2, the more it is higher, the more the soil is over-consolidated. This can be shown in another example where we knew that below 15 meters there was a heavily over-consolidated silty clay that we see very well identified by KD much greater than 2, and then above it a mixture of silts, sands, and clays with values of KD very close to 2, indicating very soft and normally consolidated material. Now, Professor Marchetti in 1980 went in several research test sites worldwide that were very well documented and identified this correlation of OCR as a function of KD. It is nice to show that additional experimental data 15 years later showed that the formula of Marchetti 1980 was very close to the best fitting line with many other additional points provided by the authors of the paper. Additional two studies in terms of theoretical and numerical modeling were published by Fino and Yu, showing again a good agreement for the formula of Marchetti 1980. This is a test site in Brazil where I had the luck to perform measurements with the Medusa DMT, and the OCR parameter evaluated exactly with the formula that I showed you was shown to agree very well with very high quality laboratory results taken by a research group of the university in Rio de Janeiro. And this is the comparison. Now, Kuretsis et al. Published a paper in 2015 with a nice collection of all these, of the correlation proposed by Marchetti, which is the black one, and additional curves published by other authors, and showing that in some soils, like high plasticity clays, the correlation with KD could be modified to obtain better results. And the same in this numerical study only, where in terms of, in case the soil is a young clay, the proposed curve of OCR is a function, again, of KD, may be plotted according to this formula. But all the results I showed you before are using the Marchetti 1980 formula, which works quite well, I would say, in over 90% of the soils. This is a formula proposed by Professor Marchetti in 1980 for K-naught, again with experimental data on site, where the test site was very well documented with valid K-naught results and showing a very, very low scatter in terms of the proposed curve. Additional theoretical work by you showed a good validation in terms of numerical modeling techniques. And again, in the same publication of Koretsis, we see additional possible correlations to refine, especially in young clays with alternative formula. The third intermediate parameter I want to introduce is the dilatometer modulus ED, which is defined according to the theory of elasticity as the elastic modulus of the horizontal load test performed by the membrane expansion. If we accept, of course, the hypothesis of elastic semi-infinite medium that we can look into this publication, it is easy to calculate ED equals 34.7 times P1 minus P0. So this is the modulus corresponding to the horizontal load test of the DMT membrane expansion. However, this modulus ED is not directly usable because it has to be corrected due to the penetration of the blade. Yet, once again, it is probably the last disturbative measurement that can be performed in situ and at depth where the soil is originally in its preserved state to obtain a modulus. Professor Marchetti decided then to provide as a modulus of the DMT the constrained modulus M, vertical drained confined tangent modulus at the geostatic stress. So to obtain this, ED had to be corrected with the other information that is available, which soil type. So either in clay, where it is undrained, it corrects ED differently than in sand, where the test is drained. And also using KD, which provides information on stress history, OCR, and especially K0, so that measuring a horizontal modulus, we can go to a vertical modulus. So these three intermediate parameters that are independent may provide the information in terms of geotechnical behavior to reconstruct a modulus M using the formula that Professor Marchetti proposed, going into many research test sites and finding the right appropriate correlation. There are many publications in literature showing excellent agreement between odometer data and dilatometer modulus. This is an example in 3 different continents: in USA, showing good agreement; in Norway, in the research site of the NGI Institute. You see the black dots are the odometer test, and the region shaded is between 2 DMT tests, showing a very good agreement and maybe even less scatter. And then in Japan, in the Tokyo Bay clay, the modulus M almost coincident with the odometer values. For what concerns the undrained shear strength SU, if the using the Schanzepp theory, I don't want to go into this detail, but just to show you the origin of the formula, using the expression of OCR as a function of KD and introducing this expression of KD into the Schanzepp relation, it is possible to obtain a closed formula of SU as a function of KD and with no multiplication factor like NKT for the CPT, but directly from KD and effective vertical stress. Again, there are several publications that may be found in literature comparing DMT results of the undrained shear strength in research test sites that are very well documented by research groups, so tests performed with high quality, high standard quality, with triaxial, CPTU, according to the NKT, and the pressure meter, showing good agreement, with the field vane test in this example in Canada, and again in Japan and Tokyo Bay Clay. This is the research test site in Fucino, Italy, where the black thick line corresponds to the DMT profile of the undrained shear strength in good agreement with the laboratory test, the field vane, and the CP2U is tuned according to the NC factor. This graph was published by Hachi in 1991. Now, thanks to the courtesy of IGS in Australia, I have additional comparisons and much more recent. This is a undrained shear strength in tailings dams in 2023. You see the the red circles are the DMT test compared with the vane test, which are the red diamonds, showing excellent agreement with the DMT, and the CPT. It was possible to tune the NKT parameter between 13 and 17 to match the DMT and the vane test. Another example, again from as a courtesy of IGS Australia, in an offshore test with a seabed of 17 meters and the depth on the y-axis, or the depth starting from the seafloor. So 5 is 5 meters below the seafloor. And as you may see, the red points are the Medusa DMT, the black diamonds, the vane shear tests, which are almost exactly the same as the undrained shear strength with the formula I just showed you, proposed by Professor Marchetti in 1980, and the CPT again with the NKT factor was calibrated between 13 and 16. In terms of friction angle, Professor Silvano Marchetti did a lot of studies with calibration chamber results and found that the initial curve had portions that were very nonlinear. And so, in conclusion, he proposed a lower bound curve that you see as a function of KD, which is this brown curve. There are again publications showing that the friction angle proposed by the DMT is in good agreement with other tests, like in this case with the self-boring pressure meters in residual soils, in this case in Hong Kong, and the residual soils were granite saprolites. The last publication on the friction angle I know of is proposed by Professor Paul Main in 2015. He showed a systematic validation of this curve proposed by Professor Marchetti using triaxial phi prime tests in undisturbed samples taken with very much care using freezing technologies and special piston samplers. And in conclusion, he confirmed that this estimation of the friction angle is a reasonable lower bound for sand strength. Now, a very, very recent publication started to propose finds a content correlation for DMT data. Since the material index ID is an indicator of soil type, it was chosen as the main parameter for this correlation, actually as the only one, ID. And in the alluvial deposit in Emilia, The points were plotted of the fine contents from laboratory and the ID from the DMT test, and Dibuccio et al. Published and proposed this curve according to xd equals to 1 and with two upper and lower bounds of xd equals 2 and xd equals 1 half for delimiting the uncertainty. On the right, you see a first example of the results, which is the brown profile, showing that it works reasonably well between 7 meters and 18 meters. It does not work very well in the surface, where it probably requires some normalization to the vertical stress and also at large depth. But it looks like an encouraging approach where further validation and study and probably refinement of the formula is also needed. Now let's look at the C reading. The C reading, we said, is the closing pressure of the membrane after it was expanded to B. So the first publication on the C reading was from Schmertman in 1988. He observed in a test site where the water level was known to be at about 1.8, I see in this graph, and he drew the hydrostatic water pressure that you see with this line. And in sands, all the C readings after correction to P2 showed to align very nicely on the water pressure, whereas in clay, they highlighted the excess pore water pressure due to the membrane penetration. Then again, below there was another sand layer, and as it approached the sandy layer, you see the C readings then aligned again nicely on the water pressure. So to summarize, when we are in a sandy material, the C reading corrected P2 is equal to the water pressure, just like a piezometer, whereas when we are in clay, P2 and UD highlights the excess pore water pressure. The UD is a intermediate parameter defined as the distance between the point and the water pressure. So in sands, UD is equal to 0 because the point is on the water pressure, whereas in clay, the point is far away from the water pressure, so UD is greater than 0. And the more it is higher, the more the soil is undrained and not permeable. So to show an example, here we are in a test site that was classified as a silty sand, so mainly with some layers also of silt and maybe some silty clay also. But the tests were performed every meter, in this case, just the C reading requires some time, so we decided to do it only every meter in 5 tests, and they very nicely showed the hydrostatic line with the known water pressure at about 1 meter. So UD was equal to 0, indicating a fully drained behavior of this silty sand. This is a recent publication by Jean Benoit at ISC7 in Barcelona, 2024, where there is a layer of sand in the top meters, then a layer of clay, and then again a layer of sand. And both BQ and UD, which are the orange and blue stars, are the BQ, while the squares and rhombus, blue and green, are the UD, are actually in very, very good agreement, in well detecting the fully drained behavior and the undrained behavior. Another test that is possible with the DMT is the dissipation test for the estimation of the coefficient of consolidation and permeability. The test consists in advancing the blade into the soil, which generates an excess pore water pressure, and then you stop the penetration and start from that time a stopwatch. The A readings taken with time will only monitor the total horizontal stress with time, accounting for how much time it takes for the water to dissipate. So there is no membrane expansion to be, only A readings are taken with time. So the graphs that comes out, if plotted in semi-logarithmic scale, draws an S-shaped curve, and the flex point that can be evaluated is then has been correlated by Totani et al. To the coefficient of consolidation. With this correlation you can read in the paper, and from there it is possible to estimate the permeability. The test is very similar to the dissipation test with the cone, Only that with the cone you measure the pore water pressure, while with the DMT you measure the total horizontal pressure and you monitor how it decays with time. But with the cone, you're measuring the water pressure in a single, very disturbed point. With the membrane, you're measuring just in front of the membrane with a much larger volume, just like a small embankment, and in a much less disturbed zone. The first evaluation of the consolidation coefficient with the DMT was experimented and published in 1998, showing a very good agreement between CH from DMT, CV in lab, and CV after the back analysis in a real project. You can read the publication in this reference. Today, with the Medusa that we will see in the next slides, it is possible to perform continuous measurements with the Medusa DMT, which is very rapid in taking A readings and following the full curve with time. And this is an example in Hungary with the coefficient of consolidation and permeability that was evaluated for this research test site. Another example is in the harbor of Barcelona, where we performed various tests with the Medusa DMT and also seismic tests. And in this case, again, the dissipation test provided a very regular curve with the flex point for the coefficient of consolidation and permeability. In this case, we are offshore with a depth of 35.5 meters below sea level. The DMT test is coded in the Eurocode in the ASTM American standards and a little more recently in the ISO standards. But there are many other national standards, and the TC16 is a document written by the committee that today is named the TC102. That is quite a comprehensive document for the DMT test procedures and processing of the results. The DMT and SDMT are used in over 85 countries today. Some are missing in here, but this map is just to give you an idea of where the test is mostly used. There are many, many points missing in Australia and New Zealand and in Brazil, but for the rest, it shows the correct distribution worldwide. Now let's go to the seismic dilatometer. The seismic dilatometer is a test that requires an instrumented rod with an electronic board inside this instrumented rod and a top and a lower sensor. The instrument is pushed into the ground and typically advanced every half a meter because the sensors are spaced half a meter. At surface, it is necessary to measure to generate the shear wave using a hammer hitting a shear beam and generating a shear wave that will travel at depth and arrive to the top sensor and then to the lower sensor. The electronic board will amplify the signals at depth, digitize them, and send them at surface so that the user will see the seismograms real time. The delay will be evaluated automatically and the shear wave velocity will be given real time, a few seconds after hitting with the hammer. This is due to the true interval configuration, which is really crucial for these types of measurements, indicating the presence of two sensors instead of only one, and an electronic board that is able to digitize the signals at depth. It is also possible to measure the P-wave velocity. In this case, it is necessary to hit the plate with the hammer in the vertical direction. This is the interface for measuring the S-wave true interval wave velocity. For example, we are at 31 meters. We click on acquisition. We are asked to energize now. We have to generate the wave hitting horizontally with the hammer the shear beam. The wave, after a few seconds, the recorded wave will appear on the screen, showing an initial silence for allowing the wave to arrive at depth, then the main shear wave, and then the tail of the wave. The software will simultaneously and rapidly evaluate the delay in the arrival of the blue and the red wave and provide the shear wave velocity vs real time, in this case 216. and meters per second, and repeating the measurement, for example, at 30 meters for 3 times, provides, in this case, a very low, and in many other cases, a variation coefficient that is very, very low. Don't trust seismic test results unless you look at the seismograms. If you receive something like this, which I received from a confidential email that I may not share with you, the sender, he commented how poor the quality of these seismograms is, and also how the arrival times were chosen in an arbitrary way with a fabricated, in his opinion, a fabricated interpretation of the shear wave velocity. And look at the noise that is here. So don't accept VS profiles unless they are provided also with the seismograms that you should check, at least qualitatively. If you use the SDMT, you should obtain seismograms of this quality, where the delay between the first top sensor, the blue, and the lower sensor, the red, should be clear and well conditioned in the period, a period and a half of the S wave. And repeating the measurement at the same depth, you should get a variation coefficient of the order of 1%, 2%, or even 3%. In clay, the waves are very smooth, like in this example. In sands, they are generally with a higher frequency, as you can see here, but the delay of the wave is very clear and persistent in the first part of the wave. In this case, also in the tail, but this is not always true. What you're interested in is that there is an initial silence, your main S wave, and then a tail, and the delay is evaluated in the main part of the wave. Here you see a test in at 40.50 meter depth from ground level with evaluations of 303, 303, 298, 298, so less than 1% of variation coefficient. Remember, the shape of the wave is not important. What is important is the delay and its consistency, which should remain persistent for the initial part of your first 1.5, 2 periods of the wave. Just to show you an example, here we are in a tailings dam in an island in Sardinia at 18 meters. As you can see here, the wave was recorded, and you can see quite a significant damping in 0.5 meter. You see that the blue peak is higher. The wave arrives to the blue first and then to the red. So there's a nice damping there, but the delay is very consistent, and the superimposition of the wave is very, very accurate, providing a shear wave velocity real time. This is a much more challenging test because we are at 88 meters depth, so more than the triple of the previous, or quadruple. In this case, the hammer has to be much stronger. But the shape of the wave has to be, again, very, very clear. Some initial noise, which is normal at depth of the order of 80 meters, then our main S wave with the delay, and the tail of the wave, and you see that the rephasing of the wave is very, very consistent, providing a VS real time. Seismic tests may be performed also in offshore environment. In this case, we are in the harbor of Barcelona with Geosciências y Exploraciones Marítimas, a company with which we commonly cooperate, owner of a Medusa SDMT, and with a hammer that was lowered to the seafloor, closely to the pipes for guiding the penetration rods into the soil at the bottom of the seafloor, we performed both DMT and seismic measurements. This is the profile of the test up to 40 meters below the seafloor, indicating with the most yellow colors, yellowish greenish colors, the sandy materials, with the bluish that are more clay material. These are the parameters of the DMT and of the VS. At 11 meters, we hit a gravel layer, and with the drill rig, it was possible to drill through it and continue below. This is the deepest shear wave we recorded, 40 meters below seafloor, and the seafloor was 17.2 meters below the water level. And as you can see, the wave is very clear. We did three measurements, 279 to 281 meters per second, and this variation coefficient is quite good in terms of percentage. Other users of the SDMT performed comparisons that you may find in many publications. This is just an example in New Zealand, comparison of VS with cross-hole tests, two cross-hole tests in the same location, showing good agreement. This is another publication, published example in Brazil with four tests comparing cross-hole VS and SDMT measurements, showing again an excellent agreement. We came across some years ago to this LinkedIn forum that was talking about true interval versus pseudo interval ways of performing seismic measurements. And they used the Marchetti, the SDMT, which before was possible, the seismic DMT, only in combination with the blade. And they said that when a seismic CPT is specified, they usually undertake the CPT first, and then they go back in the same hole with the larger diameter seismic module or SDMT to get the shear wave velocity. It takes slightly longer because you have to go up and down twice in the hole with the penetration, but less interpretation is required. So in summary, true interval is better. So, moved by this LinkedIn discussion, we decided to combine the SDMT also with the CPT. And to distinguish this combination from the seismic CPT, we decided to call it SDMT cone. So, the SDMT cone is not any seismic CPT, but it's a combination of CPT and SDMT. Of course, without a blade, just with the seismic part. We are currently partnered with three manufacturers of CPT, in particular Geomil, AP Vandenberg, and also Goda Gale, with which we provide the SDMT cone. We are currently working with other CPT manufacturers, and in theory, there is no obstacle to combine the SDMT with the CPT. Now, it's time to go to the Medusa DMT before we run out of time. So the Medusa DMT was developed at late 2018, early 2019. It is a fully automated dilatometer. It was originally developed only for offshore, but today it is used more onshore and also offshore, of course. It is composed of a battery pack, an electronic board, a hydraulic motorized syringe composed of an electric engine, a piston, and a cylinder for generating automatically and in a controlled manner the pressure. Then there's a pressure transducer and a blade with standard dimensions. The standard dimensions are kept so that all the results of the DMT may be used also for the Medusa because the device is the same, only that it is activated with a motorized syringe instead of an operator inflating and deflating with gas. The Medusa DMT does not require, compared to the pneumatic DMT, a gas tank. It does not require a control unit nor a pneumatic cable, nor does it require the operator to inflate and deflate. The equipment is very compact and it is flight transportable to any part of the world. Now, let's look at the test procedures with the Medusa DMT. The first test procedures is, of course, the standard test procedure that Professor Marchetti asked to perform. So his rules, also indicated in all the standards, is that the operator should inflate the A reading in about 15 seconds after penetration stops, with a range of plus or minus 5 seconds. And then again the B reading after A in additional 15 seconds with a possible error of 5 plus or minus 5 seconds. This type of timing is not so simple for unexperienced users, but also for any users because the gas is compressible and so you don't know how much gas you have to inflate. The Medusa DMT is a hydraulic motorized syringe that may impose with a liquid, which is incompressible, the pressurization rate. So you can actually program the time with which the A and the B readings are inflated. So it is possible to take TA equals 15 and TAB equals 15 seconds plus or minus 1 second in terms of accuracy. And this is very important because it creates like an ideal DMT test that was not always possible for unexperienced users and also for experienced users, I would say, eliminating any uncertainty related to the inflation rate. So the nice thing is also that with the Medusa, all the uh, um, many parameters are recorded. So this is the pressure. As you see for the A, B, and C readings, you see the contact is on. When the membrane expands, it goes off and it takes the A reading. Then here the membrane is expanding. And when the contact returns on, you get the B reading. The syringe returns backwards, the pressure decreases. And when the contact returns on, the C reading is obtained. So you have full control on what is going on, also in terms of the position of the piston, of the engine current to the motorized syringe. And it is impossible to overinflate the membrane due to the volume of oil that is controlled, and really, really a lot of benefits. Now, the main benefit between the traditional pneumatic DMT and the Medusa DMT is related to the following explanation. When we use the pneumatic equipment, the pressure is generated and measured at surface, whereas it acts and operates at depth with the membrane through a pneumatic cable. Since we are inflating at a certain inflation rate, it is possible that the pressure at surface is not exactly the same as the pressure acting at depth, which may provide some scatter. Now, in the past, this has proved to be very small, at least in medium to soft soils and even less in hard soils. But in extremely soft soils, this may be a problem because even a few kPa's or 10 kPa's of difference can create a problem. With the Medusa DMT, the pressure is generated and measured at depth. So there is no equalization problem of pressure along the cable because the pressure is only in this small volume and the oil is incompressible. So the accuracy is boosted to a very high and repeatable quality. This is the research type in Brazil that I already showed you talking about the OCR parameter. Now I want to show you another important point. The University of Rio performed these measurements of A and B corrected, P0 and P1, in two distinct tests, showing a repeatability that appears to be very good, and it is actually. But the soil is so soft that P1 minus P0 is a very low value of the order of less than 10 kPa. So when you subtract the values, even a small error in the repeatability may cause negative values, as you see here, and a repeatability that is not very good. This was published in a paper in 2014. Nicely, in 2018, I returned personally there to do the test with one of the first prototypes of the Medusa DMT, which highly reduced the scatter and increased the consistency and repeatability of delta P. I'm not going to plot P0 and P1 because they were right on top of each other, but delta P was also very consistent compared to the black inconsistency of the delta P of the two tests performed with the standard equipment, pneumatic equipment. And delta P is important because the material index, the deltometer modulus, and also the modulus, which is a function of ID and AD, depends on this delta P. So it's an important accuracy improvement for very soft soils, or also soils that we want to test very deep and where the cable would be long and the difference in pressure from the surface and the bottom would be too high, especially also, of course, offshore. A second possible procedure is the DMT repeated A readings test procedure. Now, this procedure consists in setting the membrane in equilibrium before penetrating to the next test depth. Then we penetrate to the next test depth, and we start taking repeated, very, very fast A readings when penetration stops, basically like a dissipation test. And then we can optionally take a membrane expansion to B, and optionally also take the C reading if B was taken. So this is one of the dissipation tests we performed in Hungary. And as you see, the data is continuous compared to the pneumatic DMT because the measurements are taken very, very rapidly. This is 100th of a minute, so just a few seconds or deciseconds, and then continuous points designing this consolidation curve. Another example was always in the harbor of Barcelona on September 2022, so offshore. And again, you see a very, very consistent dissipation curve at 35.5 meters of depth. A second possible way of using the DMTR repeated A readings is to perform the standard procedure, which requires to take the A reading at 15 seconds, the B reading at 30, and then the C readings, but also taking many A readings up to 15 seconds. Why is this useful? Because we may see from the time 0 what is going on with the pressure instead of just having one point at 15 seconds. And we can see if the pressure is stable, like in sands where it's fully drained, or in clays where it's fully undrained. But what about in silts? We have a partial drainage that may be already observed in these first 15 seconds and before expanding to B. So in this example, we did a dissipation test or repeated A readings up to 100 seconds before expanding to B and to C. So looking for a more drained response. So this programming of the time and of taking many readings with time can be very useful in the near future to test in a way that was not possible for the pneumatic DMT, and to especially in soils of partial drainage, which are typical of tailings dams. Now, I will answer the questions later. Another very, very even more innovative test procedure is the DMT while penetrating. So basically, the DMT penetrates with the membrane in equilibrium on the A reading, measuring the total horizontal stress, just like for the dissipation, but during penetration. So the A readings are plotted with depth, and the optional B and C readings could be taken, for example, every meter when we have to add an additional rod. So this is good because it's very fast with the same productivity of a CPT test, and it allows to obtain A readings with depth in a fully undrained way and not waiting for 15 seconds before getting A. This very nice publication from Danziger in that very soft site of Sarapuy, published in Barcelona, that you may decide to look into, shows 3 Medusa SDMT tests performed at a fixed penetration rate of, I think, to recall, of 2 centimeters per second, like the cone. And you see that the results are right on top of each other, showing an excellent and extreme repeatability. They performed also 2 CPT tests, showing also a good repeatability, but not, I would say, as good as with the Medusa DMT test. Thanks to the support of the EIT raw materials of the European Union, it was possible to add 2 seismic sensors in the already complex Medusa DMT for measuring also seismic waves. And this allowed to obtain also VS measurements while doing a Medusa DMT test. Now, in the remaining minutes, there are just a few, I want to show you some examples of results, and then I will hand the word to Sarah. So this is a exhibition, a pavilion in Rome, where you see there are many problems due to geotechnical incorrect design. But what I want to show you are the results. You see the A and B corrected readings, very close to each other, showing basically a clay, because we know that when the readings are close to each other, ID is indicating a clay. And when the readings are far apart, we are in sand. This is confirmed independently with this corrected C reading P2, showing excess pore water pressure, where the P0 and P1 are close to each other, indicating independently clay, and where it's sand, the C reading confirms the fully drained behavior because the C reading is on the water pressure hydrostatic line in this site. And these are the intermediate parameters, which the ID expresses the same information. Readings are close, we're in clay. Readings are far away, we are in sands, but mainly it's a clay deposit. KD shows us that KD is equal to 2 is a normally consolidated clay, except for the top layer, which I cannot comment because we don't have time. And let me show you first a pore pressure index indicating the excess pore water pressure in most layers, in the most layers of clays, and the fully drained behavior only in the sandy strata. And then the dilatometer modulus. This is the main set of graphs that I told you, the material index ID with also the colors of the chart we saw, showing bluish is more clay and yellowish or greenish is more silt and sand. The constraint modulus, the drain shear strength. In the interpreted sandy layers, we get an estimation of the friction angle, and we repeat the KD to always have close the stress history of our deposit. And then using the OCR correlation of Marchetti 1990 and also K0, we see that OCR is equal to 1 and very high at surface for what was done in the excavation. K0 in the normally consolidated soil is 0.5 approximately, higher at surface. And a dissipation test was able to characterize the coefficient of consolidation and permeability in this specific site. Another example, in this case alternating sands and clays, is this paper factory in the northeast of Italy, where you can see alternations of clay where the two readings are close to each other with excess pore water pressure, and layers of sand, like this compact layer between 8 and 14, showing very consistently P1 much greater than P0 and a fully drained behavior in terms of C reading, and then alternations of sands and clayish material. Here are the intermediate parameters, ID, saying exactly the same thing. ID, I repeat, looks at P1 and P0 and their distance and is able to distinguish the layers of clay, silts, and sands. The horizontal stress index KD, the dilatometer modulus, and again the pore pressure index, which is fully drained when it's equal to 0 and higher than 0 in finer material with excess pore water pressure. In this case, we have in the main graph also the shear wave velocity with the Medusa SDMT and the other parameters we already saw. So the stratigraphy in terms of soil behavior type with ID and the colored chart with depth. You see here the sandy layer with a higher modulus, then the undrained shear strength in the clay described layers, the friction angle in the sand described materials, and KD repeated for the stress history of the deposit, and the shear wave velocity. So to conclude this presentation, we have seen an introduction. We looked into the flat dilatometer, the interpretation of the formula with validations and comparisons with other equipment. I then showed you how the equipment of the seismic dilatometer works, and then we had an insight of the Medusa DMT and Medusa SDMT with case histories and sample results. Now that you know a lot of the equipment, I will hand the word to Professor Sara Amoroso, and she will show how to employ the results from this test for some of the most commonly used applications in geotechnical analysis and design. Thank you for your attention. Please feel free to contact me personally if you have any questions, because we may not have time at the end of this session. You can find documentation on our website, scientific documentation. Also, you may follow us on the social media, and you can find the online catalog. Thank you. Please stop the registration of the this presentation. And thank you. Sarah, can you hear me?
Yes, I can hear you. Yes.
Okay, so I've introduced you very briefly. Now
Okay.
I'll hand you the word. Simona, please start the registration when Sarah will share her screen.
Okay. Tell me if you can see my screen, please.